If you slide a heavy book across a wooden table, it eventually slows down and stops. Because we see this happen every day, human intuition tells us that rest is the natural state of matter, and that you have to apply a force to keep an object moving. But our intuition is wrong. We constantly mistake environmental factors, like friction and air resistance, for the actual laws of physics. To truly understand how the universe operates, we have to strip away the messy reality of everyday life and look at the raw, absolute rules that govern motion. This is the title page of Isaac Newton's Philosophiae Naturalis Principia Mathematica, published in 1687. Before this text, scholars often explained motion by pointing to vague occult qualities or internal desires of objects. Newton discarded all of that, replacing subjective philosophy with a rigorous mathematical framework to predict how things move. To appreciate his logic, we have to leave the real world behind, enter a completely empty theoretical void, and build the laws of classical mechanics from scratch, rule by rule. Imagine an infinite black space containing a single point of mass at rest. Newton's first law states an object at rest remains at rest, and an object in motion remains moving at constant speed in a straight line unless acted on by an unbalanced force. This means that traveling through space at a constant velocity is just as natural as sitting perfectly still. Neither state requires a continuous physical push to maintain itself. Now let's introduce an outside variable. If a new unbalanced force pushes against our moving particle, it visibly speeds up. This highlights a crucial distinction in classical mechanics. Forces do not cause velocity. Forces cause acceleration. Newton formalized this relationship with his second law, often written as F equals ma. The net force on an object is exactly equal to its mass multiplied by its change in speed over time. Because of this rule, we can encounter situations that seem completely counterintuitive. An object can move horizontally at a constant speed, even if the only forces acting on it are pointing straight up and down. Imagine a block sliding across smooth ice. Gravity pulls the block down, and the solid ground exerts a normal force, pushing it right back up. Because these two vertical forces are perfectly equal in magnitude and opposite in direction, they cancel each other out. The net vertical force is zero, meaning there is zero horizontal acceleration. But a perfect balance of forces doesn't mean the block is stationary. It simply dictates that whatever velocity the block has will no longer change. Let's take this logic further by dropping a second particle into our void, because in reality, forces never exist in isolation. Newton's third law states whenever one object exerts a force on a second object, the second exerts an equal, opposite force back. Looking at these lecture notes for classical mechanics, we see this interaction expressed mathematically. For two colliding bodies, the relationship is m1a1 equals negative m2a2, shown here by these two acceleration vectors pointing in exact opposite directions. This mirrored mathematical relationship is the exact mechanical foundation dictating how modern jet engines produce forward thrust by expelling hot exhaust gases out the back. Physicists map these abstract interactions using free body diagrams. This textbook illustration shows how we strip down a physical scenario, like a hanging traffic light, into an isolated system of pure vector forces. By isolating forces mathematically like this, engineers calculate exactly what it takes to perform incredibly complex tasks, whether that involves lifting a grand piano into a second-story window or designing an aircraft that can safely take flight. The abstract lines and equations formulated in an imaginary void serve as the exact blueprints for engineering our physical reality. Historically, these three axioms proved for the first time that the exact same forces governing everyday objects on Earth also govern the elliptical orbits of the planets. By explaining Kepler's laws of planetary motion with the same mathematics used for sliding blocks and collisions, Newton proved that the Earth and the heavens operate under a single predictable framework. Today, centuries after the Principia was published, these classical axioms remain the bedrock for everything from digital physics simulations to the massive engines propelling our rockets into space.